John R. Jensen was born in Orange County, California. He attended schools in Southern California and Utah. His bachelor's degree is from California State University, Cal State Fullerton. He received his master's degree from BYU, which is our claim on his fame, and his PhD from UCLA in geography. He has been a faculty member at UC Santa Barbara, University of Georgia, and since 1981 has been at the University of South Carolina. Presently, he is the Carolina Distinguished Professor of Geography at the University of South Carolina. He specializes in remote sensing of the environment from aircraft and satellite platforms, and has developed many digital imaging processing algorithms used throughout the world to monitor the Earth's ecosystems. He was awarded the Alan Gordon Memorial Award from the American Society for Photogrammetry and Remote Sensing for his achievements in remote sensing, and received the William T. Pecora Award from the National Aeronautics and Space Administration and the Department of the Interior, the nation's most prestigious award for remote sensing science. He is a past president of the American Society for Photogrammetry and Remote Sensing. Having published 127 journal articles and counting, and the author of the most widely adopted remote sensing and digital imaging processing textbooks, Dr. Jensen has mentored 60 master's and 31 PhD students to completion of their degrees. He has had a profound impact on the discipline of geography, and not only in the academy, but as indicated in a variety of governmental and other institutions. He served on NASA's Earth-Sun Systems Science Committee and is a member of the Mapping Science Committee of the National Academy of Sciences. Clearly a deserving recipient of an honored alumni award. He is married, as I mentioned before, to Marcia McIntyre Jensen, and they are the parents of 3 children and 12 grandchildren. He serves currently as state president in the West Columbia, South Carolina state. He previously served in the state presidency and as a bishop. Our college is pleased to recognize as a distinguished alumnus, Dr. John Jensen. Please join me in welcoming him back to BYU.
It's wonderful to be here with you this morning. I have 2 microphones on. I'm hoping I won't get electrocuted. And, I hope you can hear in the back. I do have fond feelings for Brigham Young University. I met my wife at BYU, Hawaii, and got my master's here, and was well trained to go on to UCLA. So it's I never did get to go to a single game because we were so poor, but now I get to go to a game on Saturday. So what we're going to do today is introduce you to some fundamental principles associated with remote sensing of the environment. And these are a couple of the books that I use. They have 600 pages each. Most of what you'll see today is in there. One on digital image processing, one on remote sensing of environment. And you know, when I first started out in geography, there wasn't even the word remote sensing. So in 1972 here at Brigham Young, that word had just barely been introduced. It's a very fast-growing field. So we had books that students use, and these are some 6 or 7 National Academy of Science publications that just came out. And since I came here last in 2005, we basically recommended to how the U.S. Geological Survey should use geographic principles more in their science. And also we have the latest document out about how to use LIDAR to make maps for all of the United States. And this is being used very heavily now. These set standards and practices because they come out of the Mapping Science Committee of the National Academy. And I'll show you some of the results of these publications. One of the things I like to do is structure information. And the way that people who are in charge of monitoring natural resources structure spatial information, let's say you're a forester or you want to protect the ecosystems around Utah County. Well, the Department of Natural Resources, how they structure spatial information is within a spatial data infrastructure. And we have the National Geographic Data Committee in the United States, and we have these on a global basis. We have global spatial data infrastructures. And what that means is that at the very most fundamental level, we have the surveyors running around getting ground control. And then we have digital elevation models, we have some aerial photography, and then we overlay on that transportation boundaries. Every single parcel, the parcel that you, of the plot that you own or your parents own. We have land use, land cover, vegetation, soils, etc. Anything you can think of that's spatial in nature. And we use these in this, I'm getting familiar with the buttons here, with this, we put it in a geographic information system. Now, the heart and soul of much of what a geographer does in this day and age is use a geographic information system, meaning that every one of those databases, this happens to be South Carolina, land cover, transportation, elevation, hydrology, and just an image, it's perfectly registered. Well, almost perfectly registered. So if I put a pin right down through the intersection of a road, it would go through the same road intersection in all of them. That's a geographic information system. And that's the way almost all people responsible for planning and natural resources development and protection, whether it be on the land or in the water, they use GIS. So a lot of what I'll talk to you about today is going into a geographic information system. All right, well, here's one in Beaufort County. All the counties use them also, in addition to the agencies. You know, and here they're, again, on the bottom is the geodetic control to hold it all together. Digital elevation model, a couple of infrared and natural color air photos, transportation network, the parcels. If you own a piece of land, it is at the local county courthouse. It's a parcel of certain dimensions that have been surveyed, and then there's actually the building footprints. And this is the way all of our cities are planned. It's the way zoning maps are made. So it just drags geography screaming and kicking, and we can't hardly produce enough people who know these technologies. They're called GI science technologies. Well, how do we get this information into these spatial data infrastructures? Well, you can go on the ground, and we call that in situ or in place. You're on the ground. And I just got a historical one here that, you know, it's hard for him to get around in that environment. Nevertheless, very important point measurement right here, geographer. This is one of my PhD graduates. He came, got his master's degree here at Brigham Young, went on and got his doctorate with me, Steve Schill. He's doing leaf area index, how much leaf area gives us an indication of what the yield's going to be, and then we measure that from satellite. So he's doing the ground reference information. This is Ryan and I in Utah a few days ago collecting ground reference information on the ground, in situ, because we have to use this to calibrate the satellite data. We just don't get satellite data and think we know what we're looking at. We have to know what's on the ground. You'll notice who's carrying the most heavy part of the pack and everything. He also now he's got his BYU hat on. I got my University of South Carolina hat on. Anyway, so in situ is very important. We're never going to do away with and say, we will never say, oh, we can do it all with remote sensing. Those people are foolish. We always have to have in situ ground measurement, and we better know what's on the ground really well before we try to do things with aircraft or satellite-borne sensors. Well, I love to be out in the field, and I really don't like to be in the planes that are collecting the data. I've never been in a spacecraft yet, only a few people have. But what we do is, we have airborne remote sensing systems. Suborbital means they breathe air, okay? They breathe air. And we can have aircraft, we can have helicopters. Basically, there's a sensor, and it looks down at the ground and into a certain diameter spot size. We call that the instantaneous field of view. And this spot size might be 10 meters in diameter, and we measure the spectral reflectance characteristics or the heat characteristics or the backscattering coefficient characteristics if we're using radar. We measure what comes off of there. And we get this information, we record it back here in the sensor system, and then we bring it to the ground. And we make maps from this information. And that's where the data that goes, about 60% of the data in these spatial data infrastructures come from remote sensing. People want to think it comes from other places. No, it comes from remote sensing. Okay. Now, remote sensing is obtaining information about an object without being in direct physical contact with it. You are remote sensing me right now. You have two of the best remote sensing systems ever created. Father in heaven does a wonderful job. You have two of them. You don't just have one. If you had one, you'd have monocular vision. You have two, so you're looking at me with, there's 2.6 inches between your eyes. It's called the interpupillary distance. That distance allows you to get two different views of me and look, and you can tell whether I'm three-dimensional or not. If you had a poked out eye, you wouldn't tell how good looking I am and what three-dimensional, because you just wouldn't have that binocular vision. So we have the capability to have this remote sensing system monitoring from afar. And that's very important because there's just some areas, middle of swamps, wars, deserts, inhospitable areas that you do not want to be in. So it's perfect for this day and age. It's actually perfect for any age. They just didn't have it until a few years ago. It'd be like, what if we didn't have English or math until like 30 years ago? I mean, it's that new. Whole new technologies, whole new occupations. Well, these are some of the things that it gives you if we want to look at, we get an aerial regional perspective view that you can get no other way. Human beings have a limited field of view. If you get on top of a hill, you might can see things, but even that's limited. We can go way beyond that. Imagery represents a historical document. These are fantastic things that will stand up in court as to it was this way and it got changed, and why did it get changed? A sequence of occupants. And it's wonderful to watch what people have and have not done to the earth. Three-dimensional depth perception. Your binocular vision gives you depth perception. We create instruments that give you three-dimensional views. So from these vast vantage points, we can get three-dimensional information. And we obtain knowledge beyond the visual world. Your eyes are only sensitive to blue, green, and red. I'm going to talk about extending that into the ultraviolet and into the near-infrared, into the thermal infrared. And then we get to extract biophysical information also. So there's all these things that remote sensing can provide once you learn about it and use it wisely. For instance, this is Apollo 17 photograph on the left taken by John Cernan as they were going to the moon. That's a hemisphere, a half a sphere. How would you get a half a sphere of anything on the earth? You just can't. You can go to the local hill, go up on this one above the Y, you don't get a half a sphere. You get a tiny little view. We can get the whole half of the sphere. This is called the blue marble. Things like this have stimulated the environmental awareness of Americans and throughout the world. These simple globes like this, taken on the way to the moon. By that way, this was the last group that ever set foot on the moon, 1972. Well, you've been to Google Earth now. You know about how you can get online, find my mom's house if you want. And, well, we can these are high-resolution images. We can put them all together. The Earth is not flat, you can tell, right? And we know that the Earth's not flat. We've seen it's not flat, and we can create a gridicule and put all the images and update them daily. I can find this building in about 20 seconds on my iPhone if I want to, based on these data sets. So we'll look at that perspective, the regional perspective. Also, this ability to do regional things is very important because this, I can't talk too long about these things, but this is in Zimbabwe, and there is a political person in charge of the country. And because the people who lived in this squatter city, which they call informal cities, they've sanitized it, and this is a squatter city of 10,000 people, and because they don't vote the way he wanted them to vote, he had the police come in here and demolish the whole area. Therefore, where do you think these people go? They don't go into the city, they go back out in the country, they don't vote. He completely controlled the vote. It's all written up in the New York Times on that date. This poor little boy outside his house. So we document tragedies, we document hazards that take place, but they can't get away with it because we can monitor. We can monitor, and it's there for all to see. And these photos were at the New York Times. And we're using 61 centimeter high resolution imagery. 61 centimeters means we can resolve something about the size of this here. Not your head, but at least this chair we could see. That's pretty good resolution. I'm going to define a couple of terms here just so we have them for the rest of the discussion. Spatial resolution, remember I showed you that three-dimensional little area on the ground, that diameter? That's what we call the spatial resolution. We're interested in the size of the field of view. And the general rule of thumb is if you want to find my head, you're searching for me, and you want to find my head, let's just say my head is 10 inches in diameter, then you need 1/2 the size of my head in its largest dimension. You need 5-inch diameter pixels, so to speak, to find my head. To really do a good job, you get 2 1/4. Get more the merrier, but if you want to find a car that's 10 feet, then the minimum resolution you use is about 5 feet spatial resolution. We got to match the nature of the problem with the resolution of the sensor system. So just keep that in mind. And also, spectral. Your eyes can only see blue, green, and red. A wolf can see way out in the near infrared and into the ultraviolet. Like at night, it's a different world to them. It's dark to us. But there are animals and other things. What we can do, though, is extend using sensors out into the ultraviolet and into the thermal infrared, the near infrared, so we get to get information beyond what we can experience. Temporal, we can fly these things all the time on our demand. Isn't it great when you wake up in the morning and you see where the frontal systems are coming? Because we're collecting that type of information. It's all remote sensing that's giving you your nightly news. All those images on the Weather Channel that are wrong, coming from remote sensing. Just kidding. All right. Radiometric just means we used to have the ability to measure things in 6 bits and then 7 bits, 0 to 127, now 8 bits, 0 to 255. Then we go to 9 bits. Many of the sensor systems are gathering data. It's like a really accurate ruler. It's, values from 0 to 1023 is much better than a ruler. So a ruler with 1024 marks on it versus a ruler with 64 marks on it, it's just a much more precise measurements that we get. It's getting better and better. Remote sensing's neat. They're always making better sensors. They're always making better platforms, the aircraft and the satellites, and we're always making better optical systems and computer science ways of processing the data. It's getting better and better. Here's spatial resolution. Let's just drive this point home for a minute. This is down at Hilton Head, South Carolina. If you look at this, this is 1/2 meter spatial resolution. A spot on the ground about like this, about like that. I wouldn't expect to see people's heads because it's too big. Now, if you take it up to 1 meter, still looks pretty good. Take it up to 2.5 meters, still looks pretty good. You see how at 5 meters it starts to get fuzzy? You go to 10 meters. You go to 30 meters. In a few minutes, I'll show you that most of what our U.S. government does is that, which isn't practical for urban-suburban applications, is it? But you want to do urban-suburban applications, you're going to need less than 1/2 meter, usually on the order of 2.5. And some of the things I'll show you. So you got to match the nature of your problem. If it's a high-resolution problem, you've got to use high-resolution data, and don't try to use something that's 40 by 40 meter pixels to do. That 40 by 40 meter pixels is lots bigger than this room. So when I started off, this is what I got to work with in 1972 when Landsat was launched. Wow, that was great, wasn't it? Yeah. And I've helped all through, I've given testimony to government agencies and to Al Gore and on the Hill and everything. Now we have data up here for a lot of our problems. And it's pretty neat in the last 20 years to get it. And it's available to you. It's not under lock and key by the government. Let's see. All right, now that's the spatial. The spectral, for the majority of what we do in remote sensing, except for radar and except for LiDAR, we use the energy from the sun. So we got a great, it's really fantastic. We got thermonuclear fusion taking place on the sun, giving us every day, we bathe this with electromagnetic energy. It's pretty constant. It's not totally constant because of these big prominences that blast off and just irradiate the universe. But here it comes, and we know from Sir Isaac Newton, we can take that energy, that, in effect, wavefront of energy and break it into its spectral components. And if I break it into its components, it's just like this. Blue, green, yellow, orange, red. That's what will happen. And so I'm broken it out here. These little lines and things in here are the Fraunhofer areas where it kind of shuts down. But your eyes are only sensitive to the blues, the greens, the reds, this little area right here out of the whole enormous electromagnetic spectrum. Thank goodness for that, because this is what the sun produces most of. So our eyes are these wonderful remote sensing systems. We use a lot of remote sensing in these areas. Now there's energy out here beyond it, and beyond the red, infrared, there's energy below it. And we have sensors that measure in those areas too. I'm not going to talk about all those today. But just keep in mind, this is you. Your eyes can see blue, green, red. Now, if you don't see blue, green, red there, see me after class. You're slightly colorblind. And there's a test I can give you to tell you why you wear funny clothes and things. All right, so now this here, we take that, you have a fingerprint, and if you do something wrong, they can find you because of the fingerprint. Well, this is the way that, if I put blue, green, red, near infrared on the x-axis in wavelength, and I put reflectance on the y-axis, it's like a signature. It's like a plant. This is the signature of a healthy green plant. You have a signature. Well, this is the healthy green plant signature. It says, I suck up almost all the energy from the sun in the blue region. I love it for photosynthesis. I use quite a bit of the green, but I still reflect quite a bit of the green. I don't use as much. And I love red light. I'm a plant. This is my signature. I'm going to suck up as much as I can get. And I'm going to get rid of as much of this near infrared energy as I can. That is a plant's signature. All right? By the same token, if I'm clear water, I will reflect quite a bit of blue and quite a bit of green, and I'm not going to reflect much red, and I'm going to hardly reflect any near infrared. This is my signature of water. Now, what if everything had exactly the same signature out there? The soils, the vegetation, the rocks, the asphalt, the concrete. Then all the curves would be right on top of one another, and we wouldn't be able to discriminate them. But the beauty of it is, look how different these things are. Concrete, high in the blue, high in the green, high in the red, that's totally different. If I had a sensor that only recorded that exact point, I wouldn't be able to discriminate the two. But anytime there's big differences like this, that's the beauty of remote sensing. There's like a signature associated with these phenomena in these blues, greens, reds, near infrared. And we measure way below here into the ultraviolet and way out here into the thermal infrared. We have lots of energy to work with. You might say, what? I don't understand that. Okay? Well, this is a satellite image of some area in the Mideast. And this is, if I only recorded the green energy, it looks like, because green plants suck up most of the green energy and they don't give much off, so it looks dark. It's a heavily vegetated pixel. All these look these are center pivot irrigation systems. Looks like that's really a good producing center pivot area. And the same we look in the red. Remember, plants absorb a lot of red. They love it. Suck it right up, therefore it shows up very dark in the imagery. But in the infrared, which it reflects, if there's a lot of vegetation there, it reflects a lot. We can see here now, this isn't really got very much vegetation in it. But this does, and this does. These are healthy. So when I put the color composite of this one, and this one together, this is what we call a false color composite. We do it all the time. This shows you where the healthiest vegetation is in these center pivots. This one isn't doing very well at all. I'd be completely confused if I only had red and green, because it looks, but also notice the subtle things in here. This is the way we tell farmers where they need to apply fertilizer, where they need to apply water. This is precision agriculture, and it's just taking off now in terms of the use of remote sensing for precision agriculture. 10 years or 15 years from now, they'll have UAVs, unmanned aerial vehicles, that the farmer can just fly over all his crops, and it'll tell him where to water, where to fertilize. Maybe I better move it to 20 years from now. Maybe they'll do it by satellite, but we haven't done it. We've been working on this for 20 years. We always do things that never... It takes a long time to get things into the mainstream. But Monsanto companies and John Deere, they've got all these precision tractors that will put the fertilizer out exactly based on what's in the image, so that they don't waste their money on areas that are already good. Makes so much sense. All right, now I'm going to talk about an overview of aerial photography, both analog and digital, briefly about multispectral scanning systems, hyperspectral. These are all terms you probably thought my friend Tim Ivey said, you just make those words up, don't you? No, I didn't make these words up. These are scientific words based on the fundamental principles. LiDAR we're going to talk about. I probably won't get to thermal infrared, but we'll move along. So let's talk about aerial photography. You can relate to this. You've all owned a camera. You all owned a camera before it was digital, right? Film. In the back of that camera had film, silver halide crystals. That's why film costs a lot. It actually has real silver in it. If you got enough of it together, you can melt it down and turn it into a bar. It's silver. That's why it was expensive. Well, you know, Kodak's not that thrilled about all this because they've had to move totally now into the digital world, but let's stick with the analog world right now, analog film. It's also the energy from the real world passes through a lens, and up here, it's a reversal of tone and geometry. You ever wonder why all these colors are up here? Down here, it's blue, green, and red. Your negative was always yellow, magenta, and cyan dyes. Yellow, magenta, and cyan dyes, and they looked weird. You had to reproject them and expose paper. That's a reversal of tone and geometry up here. Well, the history of this, I'm going to do for a minute. This was the first person ever to create a photograph, okay? And he's world famous. You know, it was a big day when suddenly you could record something and it would stay. Because up to that time, you could only have an artist draw. You couldn't make anything stay, so he gets a plate. He puts bitumen of Judea on it, which is like an asphalt, and he exposes it for 8 hours out his window, and then he fixes it, makes it permanent, and that is the first known photo ever. It's not air photo, it's just photo. And I have to pay $300 to use this every time, so I'll turn in the bill. I'm just kidding. $300 for my book. And this is the guy, and it's a French estate. He's looking out his window. Can you see that it's something? It's kind of hard to tell, right? It's an outdoor view. So this guy, though, is another real person. He's an artist in France, Gaspard Phoenix Chernachon. And he really does have legs. He's just kind of kneeling down in the basket. And he went up, took his balloon in 1858, and took the first air photos ever. That's the beginning of remote sensing, and in a Hippodrome balloon in France. And so there's our very first air photo. I have to pay $300 to use this photo also. So, because it's copyrighted. And 1,700 feet's pretty high up. It's not just like your little balloon. And he's up there, and he took it from the Hippodrome balloon in a multi-band camera. Pretty sophisticated. All right, let's look at that for a minute. Remote sensing people will use anything to get airborne. So this is a castle in Germany during World War I, and what do you think took it? Bird. How are you going to train? I can't train a bird to do anything. So, okay, this is the way they did it. And these guys actually got medals in World War I for doing the work. When I was a boy, my mom and I and my brother, my son had pigeons, and if you have a real homing pigeon, you put a 70-gram camera on it. We never did. And you take it in a secret place, and you let it go, and it will go like this. And you have it so it's clicking off exposures as it does that. And then it will go home, because it's a homing pigeon. And that's what they did. And they got secret information out. I mean, kind of ridiculous, but it really did work. You know, Scientific American, the journal, Scientific American, in 1903, you can go to Scientific American. There's a whole article on how to do this. So, you know, it seems stupid, but I like it. So, it's a whole squadron of them there. All right, now finally, we don't have to use pigeons. Same year, interesting, 1903, we get a heavier-than-air platform to put our remote sensing systems on that has a 13-horsepower bicycle engine. And they're Kitty Hawk because they can have the good lift. Where I live in North and South Carolina, and Orville Wright's in there, and he didn't know how to control this thing. They were always crashing. You have to take your hats off to these people because, you know, it's not like flying now. And then things get better. The planes get really good. I want you to look at this guy. He's carrying a very large camera, probably weighs 100 pounds. He's not so excited about this. And look at the pilot. He's all excited. And I don't even see a seat belt and lots of protection for them. And that's the beginning of, and this is a Curtiss AH-13, the very best plane we had in the beginning of World War II, World War I. And these were used heavily. And we've got photos of the Maginot Line where all the millions and millions of men fought and died between these deep trenches, and they would use the air photos to find out where they were and make their tactics. And it was the first use of aerial photography for warfare. Very heavy demand. Then in We know we used them heavily and more heavily. In fact, Werner von Frisch said at the beginning of the Second World War, the countries that all have the best aerial reconnaissance will win this war because they know where the materials are, they know how to make their tactics. And we had very little in the beginning and really good at the end. And I was mentored by a guy named Bob Caldwell, who was in charge of all the US's getting better and better and better in photo reconnaissance. And in this particular one, you can see sad thing about war. Here's some bombs from a plane up above knocking off this horizontal stabilizer, and this plane would probably crash because these bombs fell through it. They're bombing Paris, and they do a lot of bomb damage assessment. I don't do military work. I won't talk about that, I guess. We have the U-2. In the 70s, part of the Cold War. I could barely fit in this fuselage. I've said it before. You got to be skinny, and the wings are as wide as this room. Flew right up where there aren't very many molecules left, suborbital. And they acquired data like the Cuban Missile Crisis. Now, my mom is here. This is the actual photos. These are the actual photos obtained. You can't see it real quick, but the oxidizer trailers, the actual trailers. This is Cuba. These are ballistic missiles in October of 1962. And this is the dialogue over here about Mr. Youngdahl giving the photos to the president. And we almost went to war with Cuba over these. And for those of you who were alive then, my brother and I, we were scared. Everybody was talking about it, so we went out in the backyard, started to dig a bomb shelter for about 2 minutes. We got tired of that and did something else. But it was a real scare. My parents were scared. We didn't know if the world was going to blow up. It was a very scary time because it was nuclear weapons going to be exchanged on American soil between Cuba and China. It was all documented by, in this case, the U-2, and then this is a different type of aircraft, an RF-110 that got this one down here. So military reconnaissance, it's huge, used all the time. All right, and then we got better reconnaissance planes. The SR-71 flies faster than a 30-06 bullet, go clear across the United States in like 20, 30 minutes, and still the fastest thing up there. And they occasionally drag it out and use it. All right, then finally, we got things up in the air. We can't keep flying over countries and be shot down like Gary Powers did in the U-2. So finally we get a spacecraft up there, and this shows where the Russians were doing a lot of above ground testing. We document that. And this is interesting because this is the very first image from space, remote sensing. Not very high resolution, it was acquired by this. And this system up in space actually kicked out little packets of film out the back of it. And the plane would have to come along and grab the bag that had the film, or it went in the ocean. I mean, completely ridiculous, right? But that's how it did it, and that was how it was produced. So that's our first satellite. It would drop things into orbit, and you'd pick it up like that. All right, that's the history. Now here's what we do today. If we're going to do suborbital, I'll get to orbital in a minute. This is a typical plane. These are the tires. Tire, we're looking at the underside of the plane. That's a camera mount, that's a camera mount. This is what an aerial mapping camera looks like today, run by an operator. So it's not your camera stuck in a plane, okay? You have to have an FAA approval because you don't want this 500-pound thing falling through your house out this hole. And so we have very sophisticated, I'm a certified photogrammetrist, I'm a geographer, I'm a certified photogrammetrist also, to do this type of mapping. And it's not hard to become one, just a bunch of classes. And we can take photos that look like this. This is if you stuck your head out of the window in Beaufort, South Carolina, it would look like that, blue, green, red. If you were a wolf and you knocked off the blue, it would look something like this. That's a natural color, color infrared image of the same area. Now, what we've changed to and we've migrated to, especially in the last 5 years, is this. We used to all be analog, and now all of these companies throughout the world are moving towards digital. Now you can relate to this. You have a new digital camera. Only these are big digital cameras, and we basically have banks in it, blue, green, red, near infrared. We may have a whole bunch of bands in there now in these very expensive digital cameras. So now we get imagery like this. Your county is flown like this with digital cameras now. It's stockpiled probably by your local planning commission or the Utah Department of Natural Resources. 1 foot resolution really good. And we even get better than that, as I'm going to show you in a minute. I put this in here because even in 1899, people knew how to take one photo. It was a camera like this. It had a camera here and a lens here and a lens here, and it would take the same photo of the same thing from two different vantage points, just like your two eyes. You're going to get binocular vision, stereoscopic vision. Now, this isn't airborne because we didn't have any airborne things going on then, but we always get overlapping aerial photography. Each successive scene in the air photo flight line is 60% overlap on the previous one, so we get to look at, the arch in St. Louis or the Capitol from slightly different vantage points. You see how it leans one way this way and one way this way as you fly along? It has to. You get two different looks at the same feature, and we look at that in stereo, like this. And this is the traditional method of analyzing air photos. You can do it. It's pretty easy. It's fun. It's what got me into this whole field. I said, do they pay you for doing this? And they said, yeah, they'll pay you for doing that. And I like to make maps. I said, do they pay you for making maps? And so cartography and air photo interpretation. And then I was standing there like with my bags, and it turned into remote sensing, and still in its infancy though. So we still do this, but now we do what's called soft copy photogrammetry. Hard copy is a real hard copy photo. Soft copy is digital. That's why we call it soft copy. So now, bear with me here for a minute. This is the screen of one of our soft copy workstations. And I'm not giving you mathematics today. I'm just showing you how things work. But basically, up here in the corner, that's a 9 by 9 inch photo. So the photo is 9 inches by 9 inches, photo number 1 of Columbia. This is the 9 by 9 inch photo number 2. It overlaps this photo by 60%. You maybe can find the same building in here. Overlaps by 60%. I can zoom in here to the left photo. Here's the Capitol. Zoom in here to the left photo. Here's the Capitol. But there's this little park area here with right here is a fountain. That same fountain's here. And then it's blown up right up here, and it's blown up right up here. It allows me to orient and scale this stereoscopic model to where I can eventually get to look at it. And have any of you been to movies lately, like The Mummy or something, where you wear those glasses, the anaglyphic glasses? Same thing we do. We put them on, and we're able to see this in 3 dimensions. The buildings, they just stand right up, 3 dimensions. And we put what's called the floating mark. We adjust the cursor, and it takes the floating mark, and this cursor can be like the floating mark. We put that floating mark, it looks exactly like this. If I want to make a map, I just draw that right around there like that. And while I'm doing it, it creates the exact planimetric footprint of that building. Or this road, you just do a center line of the road, etc. It's the way we do contours. And if I want to do contours, I just put it on 100 foot above sea level and follow it around as long as I keep the floating mark on the ground. That's the way all your maps are made, photogrammetrically. It's not, well, there's some surveying that takes place, and you can make them by surveying, but the vast majority is now with soft copy photogrammetry when you see topographic maps by the U.S. Geological Survey or any other company. This is Richland County. I'm sure your county here, the Utah County, whether you know it or not, every one of your homes has a building footprint. Every one of your homes has a parcel. There's your parcel. And that's a legal description. It's one of the things about America. We have cadastre. We have a legal description of your property and a building footprint. In Africa, you don't have that, and what's one of the biggest things we're trying to get Africa and other places to do, because how can you ever own anything if nobody ever has a legal description of it? So just having this is very protective and powerful, and remote sensing is helping in that regard. So this is my county. We get really detailed information out of air photos. And we can, without ever having gone to some city somewhere, I can get the air photos, I can generate a 3-dimensional version of that city. And that's great for geography. You can sit in your armchair and be an armchair geography, yet as I'll show you in a few minutes, you can create a landscape. You can know everything about it almost without having been there. If you're a geomorphologist, you can create the mountain range and go study it 3-dimensionally, virtually. And you can do it yourself. You don't have to wait for Lucas and Star Wars to do it for you. So Let's see. We can take that information and make three-dimensional cities. All right, now I want to introduce something I didn't talk about a couple of years ago when I visited here, pictometry. I'm like a pure photogrammetrist, and we usually don't like to use oblique stuff. That's all changed in the last couple of years. I've had to reevaluate my thinking because pictometry, let's look at that. What is that? God, really good people. All right. Anyway, that's a glass, right? It's a lot easier to interpret the oblique view than the vertical, isn't it? All right, well, here's another one. Let's look at the bottom one. Look at the bottom. Oh, sorry. I'm not familiar with this, but look at the bottom one here. Okay, this is parking. This is a boat that they pull right up to the shore because you can't gamble in Mississippi, but you can gamble in the water. So it's 1 foot offshore. They put the planks. This thing used to be over here. Beautiful hotel here, beautiful hotel here. Now, a lot of my NASA conferences are held here because it's near NASA base St. Louis. And during Hurricane Katrina, this guy got broken off and went over here. Well, it's much easier to appreciate it obliquely. Okay? People, you're looking at me obliquely. If you look at if I walk around and all you can see the top of my head, it's not that useful. It's not even that attractive. But if you obliquely, you look at the facade of things. So we're finding that even though the scientists, we want everything vertical, the people are going, we don't care about you guys. We want it obliquely so it's easy to interpret. And that is easy to interpret versus that. Okay? It's a beautiful hotel. It was a beautiful hotel. Okay, so we have a new technology called pictometry. Here we have one vertical camera that looks straight down and a camera that looks east, south, west, and north. And every time it takes one photo, it takes five. So you're getting this tremendous amount of oblique at 45-degree angle also. And so if this is the area around my campus, one of our new buildings, the Solomon Blott Physical Education Center, looking straight down, that's a typical vertical. We also get these four other ones. And every single exposures, you can imagine how many views we're going to get of things when we do this, when we fly flight lines. And so, but look at the detail on this, 4-inch resolution. Okay, just fantastic. And they're doing this county after county after county after county now, moving towards getting both the vertical and all the obliques. And here's what it looks like. Here's why they like it. For all these different 911 applications, it's perfect for geography. It's perfect for the medical profession because they get an alarm. The first thing the guy does is bring it up on the screen, finds out where it is, picks out which of the photos he wants to look at, and they're all over here of this area. It's all in a geographic database. He pulls up the photo that he wants. He looks at it. What kind of equipment should we bring to this? What if I bring the wrong equipment? Well, we'll bring it up. Here he's doing hard copy, but he brings it up. He can put his cursor right there and go like that. It'll tell him that building's 64 feet. We got to take the ladder that's at least 64 feet to save people's lives. If he gets there and he took the wrong ladder, people die. So they use it for lots of different purposes. And it's also an intelligent map. All these things in here are in what we call an intelligent GIS because all you got to do is point and click and get information. All right, now I want to show a quick video. In the past, creating synthetic three-dimensional cities has been really hard because for every building, we only had the rooftop characteristics. And we used to go to elaborate lengths to get the facades, the sides of the buildings to make them look right. Well, with having all these new oblique and vertical photos, remember 1 vertical and 4 obliques, we now have all this facade information that we can put together. So this is all done with pictometry data. Now just look at the detail as it goes through here. There's the underlying three-dimensional structure underneath it. I really like right here the detail. The facades here, we don't have to make them up. They're done, they're input from the oblique views. So anywhere in the world, and you can imagine why the military is interested in the technology, but I like to use it for peaceful purposes, for urban planning purposes. Now sometimes the cars get squashed in this. because we don't work on making them. But it's just phenomenal. And you can lay out your course and fly through anything you want, and it doesn't just have to be urban. It could be Mount Timpanogos, low and slow all around it. It just does not matter. But the detail now is phenomenal, and it's a combination here of probably the pictometry data and the LiDAR data. That's good, Ryan. I'll do some more, but we don't have that much more time. Okay. Got about 12 minutes. I think I'm going to skip, maybe Ryan help me out, because I don't have as much time as to go through everything. I'm going to skip and go, let's go to the LiDAR. It's in the next one. LiDAR is a brand new technology, and we've introduced air photography, analog and digital. Keep going down, it's right there. Next one. Next one. There we go. All right. Now, LiDAR wasn't even around 20 years ago. And it's revolutionizing the way we make our digital elevation models and make our contours. And basically, we don't have a good LiDAR in space yet. I'm on a number of panels. We're trying to get one from space. Keeps getting killed. GPS on board, a GPS unit on board. We got to know where the plane is. The inertial measurement unit on board tells exactly what the plane's doing in terms of roll, pitch, and yaw. Roll, pitch, and yaw. And it keeps track of that because every second it's sending out all these pulses, like maybe 300,000 pulses of laser light. 300,000 every second. All right? And these beams down here illuminate an area on the ground, and depending on what they hit, they send energy back up. All right, so here's a LiDAR sensor, a typical one. I ordered these up for my different projects. And I really don't like to be on them because you can get sick on them really easy. Because they're always going like this. They're all over the place. But here's the logic of LiDAR. It's light detection and ranging. All right? It sends out a pulse of electromagnetic energy. It's 1040 nanometers, which is near infrared light. It's not going to hurt your eyes. Comes down here. If it doesn't hit anything, it interacts with everything here and sends a pulse back. It's all about timing. This is a ranging device, just like radar. All right, so our first and our last return here may be very similar. We send out another pulse here, but when it starts interacting with the trees here, it gets a return. Interacts with this part of the tree, gets a return. Interacts with here, it's the bottom. And when we're going to make a bare earth digital elevation model for hydrology or for city planning, we really want to know where the bare earth is. But the foresters love the information that we get from within the trees, all the structural information. So this will have a first, a second, on the last return, and we can model these. So I'm going to show you some areas done on the Savannah River site. These are some high priority hazardous waste sites. These are some test sites right here. I'll show you. Next slide. Oh, me. This is what those test sites look like. There's just 5 of them. 1, 2, 3, 4, and then another one over here on the side. They're just little mounds, but they're very important. They try lots of different experiments out with regard to them. So here's my LiDAR data. Here's my first return LiDAR data. There are my mounds right here. You can also see this is another big hazardous waste site that's smooth as the baby's behind. It's just flat with grass on it. You can see the trees. You'll notice this big feature here is not in this one over here because that's the first return. This is the last return. If I difference the first and the last return, I get a bare earth. It takes off all the buildings. It takes off all of the vegetation if we do it right. This is what we make our digital elevation models out. We don't want to be contouring on the trees. And this is so much faster, so much more accurate than any other ways we used to obtain digital elevation information. This is what the data actually looks like, the LiDAR data, for that areas over those four mounds. Every one of these points, that one point there, is the equivalent of me sending out a surveyor with a GPS unit and getting a point at that location. And this one happened to send out 70,000 surveyors a second. 70,000, 70,000, 70,000, 70,000, 70,000. You see how fast it is compared to sending out? For me to get 10 points a day by a surveyor is a big deal, $1,000 a point. These things send out now 300,000 points per second, the new ones. So this is the area. This is what the data actually looks like when we turn it into a rasterized elevation surface. I can analytically HAL shade it with some of my cartographic techniques if I want to bring out the trees. Now I use the bare earth. Look at the accuracy of the bare earth contours here. These are 25 centimeter contours. So 25 centimeters is about a foot. So every foot, this is a contour. It's the most accurate way we get now to produce topographic maps that you use for earth resource mapping. If we take this same digital elevation model, we can also color code it to something you're more familiar with. You see the contours? Lines of 0.25 meter elevation. And here's the legend that I made the other day for it. Because people like color, easy to interpret. It's revolutionizing our cartographic mapping capabilities. It's easy to know where the steep parts of the terrain are. In this case, we can generate slope. The yellows and the reds, and especially right in here in these other areas, those are the steepest slopes. So we can turn the elevation data into a slope map. By the same token, just stare at that for a minute. It's going to jump around on you a little bit. But I don't know if you know it, but on certain mountains, because of the moisture regime and the insulation regime of the sun, only certain vegetation types grow on certain slopes. North-facing slopes, south-facing slopes, east-facing slopes. That's called the aspect. And so we're very interested for any three-dimensional surface. For instance, we might want to know where all the north-facing slopes are because that's where the red-cockaded woodpecker lives. All right? These would be the north-facing slopes. That makes sense. North-facing slopes. But if maybe a different type of vegetation only grew on west-facing slopes, then they would have this tone. So easy to derive this from our digital elevation model, which was developed from LiDAR. All right, well, we're very accurate at this. Here's a bunch of ground control points that were obtained. We use our equations. I hesitate putting these in here, but the bottom line is how accurate are we? 6.6 centimeters in X over this whole region. That's how much we might be off. And about this much in Y. Okay, that's a far cry from the 10-foot contour intervals and the 20-foot contour intervals on typical maps. So we've revolutionized our ability to acquire really high-resolution data. All right. I'll just show you this one more thing. Almost done. But we also get intensity data. This is first return, last return, how intense that pulse is coming back up. And it looks a lot like an air photo if you notice there. I'm going to look at this one particular tree. And so here's this tree, intensity. I color-coded the intensity. Then I draped the intensity over the digital elevation model. And lo and behold, there's structure in the tree. And foresters go crazy over this because they want to know what's going in the tree and whether this information gives them information about the basal area, whether it should be harvested or not. So foresters are really interested in LiDAR data, not for the bare ground, but for the vegetation characteristics. Also, we've got I did a master's thesis with a student who just used the LiDAR data and the intensity data to map the buildings in pink, the trees in red, and the bare soil in green, untouched by human hands. You can use a certain number of algorithms to do it. All right. I put that in there because I thought that's the Serengeti Plain in Africa. Mark, Ryan, my son. The last slide in the whole thing just has something fun that I'd like to end on. The one, no, not that one. Up one more. That one there. This is new technology that I may have said this when I was here back in 2005, but this is new technology. It's scary because they have them all over the place now, and they have them in trucks. But basically, this is if you go to the doctor and you broke your arm, they have the x-rays to find the hard material that's broken so they can see where your break is. Well, this is a new version of x-rays, and it's meant to find the soft material around, you know, your skin type things, biological type things. And so they have trucks that will now go drive by and literally, you know how thick those containers are on the trucks, right? It'll pass right through an engine block. So here's my point. For my whole career, until 2 years ago, people say, well, can you see through houses? I'd say, no, we can't see through houses. This isn't like James Bond and stuff. It's not true anymore, okay? Because the DEA and other people at the border are scanning the trucks, and the people hidden inside of the trucks, really well hidden, I'm telling you. I'd hate to be in there, wouldn't you? Horrible. Because anything goes wrong, they may just forget about you. And breathing and whatever, completely dark, maybe they have flashlights, and couldn't make a sound either or give yourself away. But anyway, this system will pass right through and find out you're fleshy. You're going to show up just like the bananas, and you're going to show up, well, the engine block doesn't show up much. But this is drugs that were hidden in they'd have to clean out the whole thing. This is the kind of nitrate that blew up areas in the Midwest that they found. They're doing this at borders. I want to do it. I want to take this same truck and pull it apart, put it in a light aircraft, and when we have Hurricane Katrina and the people get trapped in their roofs, I want to put it over every house and see if anybody's trapped in the. I want to use it for that type of purpose, and I have a proposal in to do it. But it's just a matter of time till. So now you have to go home and you have to get, I don't know what you'd get to keep them out. But that's scary to me. And remote sensing can always be used scarily or friendly. It's always had that double-edged sword capability. Well, with that, I think I'll conclude. Thank you so much for having me here today. I love BYU, and it has a great heritage, and I think it's Father in Heaven's greatest institution on the earth, and I hope you keep it that way. And I say this in the name of Jesus Christ, amen.